Hello, I am Rand Dixon. I'm here to share with you the final presentation from Capstone 1 at the University of Wisconsin STOUT. On the team was Anna Finnegan, Ben Helland, Abdul Majid Al Murwani, and myself, Rand Dixon. The project was sponsored by Ben Bogle in partnership with Hope and Mercy Mission. So I'll be sharing our mission, the path we took to our current design, our final design, a analysis of the critical components, an economic rationale, a design for manufacturing considerations, and the final recommendations. Our mission statement was to design a self-sufficient, lower-cost mobile primary care facility for construction in Uganda with local supply lines. So I want to break that down a little bit. It needs to be self-sufficient, as in it doesn't need outside anything that's going to not be available in the village. It needs to be lower cost than current solutions. It needs to be somewhat mobile, being able to be taken in and out of the village as necessary. And it needs to be constructed in Uganda using local supply lines to support the local economy. So the reason that we took on this project is that in Uganda, 70% of doctors practice in the urban region where only 20% of the population lives. That leaves only one doctor for every 22,000 people in the rural areas. This means that long travel distances in rural areas discourage patients from seeking professional care. Two of the primary health concerns in Uganda are diabetes and hypertension. So the political climate can change rapidly, so a clinic that can be moved is ideal. So some of the problems that we ran into is that country is landlocked, which makes shipping very expensive from, say, America or Europe. It gets heavy rains, around 50 inches a year. The roads are narrow and unpaved in the rural areas. There's lots of dirt and dust, which are turned to mud during the rain. And it's very hot, on average 77. There's no electricity in the rural villages. So some of the specifications that our clinic must meet is it needs to traverse the small, muddy Ugandan roads. It needs to meet or exceed the Ugandan and World Health Organization health codes. It needs to cost less than $45,000, and it has to have refrigeration at all times for medications. It should be infection control compliant, which primarily means non-porous surfaces. It should be self-sufficient when in terms of energy. It needs to be ventilated, which the WHO defines as 160 liters per second per patient. It would also be ideal if it has UV light to constantly disinfect all the surfaces. It should, and ideally would be have filtered air and positive pressure. All equipment should be locally sourced or use local supply lines. And there's a lot more requirements, but these are the most important that we would share. So if the clinic is going to be mobile, it needs to be in some sort of platform. So we thought of putting in a shipping container, in a truck, in a tent, or in a bus. So we used a decision matrix to decide which platform to go into so that it wasn't just an arbitrary decision. You can see on the left here are the criteria or constraints. It needs to be mobile, it needs to have space, it needs to be not too expensive, it needs to be very durable, it needs to be secure, and it needs to have staff. And what we mean by that is in the villages, there's a village healthcare worker, but if you're to have something mobile to stay traveling every single day, you'd have to provide staff for that. And so then we weighted each of those criteria, and then we ranked each option on each of those criteria. Then we multiplied the rating times the weight to get a weighted score. When the weighted score is tallied, you can see basically a number that's how good the option is, and then based on all of these constraints. And so the shipping container, based on these criteria, is the best option. The next decision was what power source to use. So we could use solar, we could use a diesel generator, we could use a wood burner. So we have another decision matrix. In this case, the important things are the cost, the lifespan, the reliability, the electrical output, the cost of fuel, and how much space it takes up. So we weighted them, ranked them, got a weighted score, and diesel generator and solar came very close, and we even considered doing both, but we decided to go with solar. So then, using a shipping container, it needs to have some sort of foundation. So options are a strip concrete foundation, a concrete slab, a concrete pier, or using wood. We have another rationale decision matrix. The cost, ease of construction, durability, and security were the most important features here, with cost being the driving factor. And so then by that, the wood and gravel and the pier are pretty similar, but we decided to go with a pier because it's going to be more secure and it's going to last longer. So next, we're going to get into the actual design of the clinic. And the clinic needs to be solar powered. And so we made these panels, which are made out of welded steel, and they'll fold out. And the reasons for that is primarily to allow more space to attach solar panels, but it will also provide shade for patients waiting to be seen. And when they fold in, the clinic can still be moved, so it won't adjust the mobility, but it adds security, because when the panels are folded, they can get locked shut, and that will keep them from getting damaged or stolen while the clinic is not being used or during a storm. So some more overall design. It can be relocated with a truck, so it meets the mobility needs. It has 18 solar panels, 3 12-volt Life PO4 batteries, and a power inverter. It's insulated using closed cell spray foam and has a pier foundation, as you can see in the SolidWorks image here. So you can see the floor layout in this image. The medical equipment that's involved is an exam table, an electrocardiograph machine, an oxygen concentrator, an autoclave, an ophthalmoscope, an otoscope, and a procedure light. This is the minimum that we found would be necessary for a regular operating clinic for regular checkups and regular procedures, but this could be adjusted to be more or less depending on the needs of the specific village or location where this was implemented. And you can see the UV lights are the blue on the wall there. So then this is the other side of the clinic. It has a sink there with 60-gallon or a 70-gallon water tank, which would allow the healthcare worker to wash their hands 70 times, because it takes about a gallon of water, which is very important that they be able to do that between every patient and even more often. It has a 12-volt DC pump, a water filter, and it has hose connections so that the drain water can be taken away from the clinic a significant amount and drained safely. And then it also has a connection to the outside where the tank can be filled up with either a hose or with watering cans. There's also, as you can see, lots of storage space and a fridge and cabinets. So the design has a ventilation system and an air conditioning unit. The AC unit would be on a microcontroller that, if the batteries got below 50% or whatever the operator decided, that could be programmed, then the AC would shut off. That way it doesn't consume too much power. And for a really low cost clinic, the AC could be removed altogether. It has lots of storage and workspace and an free-flowing floor layout. It has overhead lights and UV lights. So here's a picture from the outside. And here you can see what the front and back look like. So there's a fire extinguisher and lots of safety features. So then I'm not going to breeze over the engineering analysis, but if you want to, you can pause the video and then analyze each of these slides. Basically, we were concerned that as wind blew on these panels, that the stresses in these poles would be too great. And so we analyzed both the pin and the pole for buckling as well as stress. And so here's the equations that we used, our assumptions, our free body diagram, and more equations. So here's the bending and moment diagrams, our finite element analysis on the pin and those results, the conclusion from all of this is that the safety factors were high and the difference between hand calculations and computer simulations was small. So we are very sure that the clinic is not going to break. These will last. So now for the design for manufacturing rationale, we assume that the cost of products in Uganda is going to be similar but a little bit cheaper than US costs, that power tools and a portable welder will be accessible in Kampala or whatever city this would be built in. And we assume that this would be small scale production, so casting or automated production lines and other large scale production methods will be unnecessary. Parts will be bought from local supply lines and fabricated to tolerance, and then welded to make assemblies. So we're assuming that power tools, a welder, grinder, that sort of thing, but nothing more complicated than that, no machining or anything like that. So now for the economic analysis, the lowest current price for a product on the market that's similar is Clinic in a Can, and it costs $45,000 to purchase in the United States, and then there's an additional $20,000 in shipping to get it to Uganda. So to build a clinic in Kampala, we estimate that the cost of materials will be about $40,705, and the cost of labor will be about $2,295, which brings the total manufacturing cost to $43,000. So the design is structural, it does meet the criteria, and based on our estimates, it is financially feasible. What we recommend is that someone, perhaps myself or one of our partners in Uganda, takes our bill of material and finds the actual cost of all those materials in Uganda. Assuming the project is still financially feasible, then a team of volunteers should go over, and that would include myself and probably others either from this Capstone 1 team or other volunteers should go over and build a prototype. That prototype should be brought into a village and used for 6 months or so, and then the design should be updated based on what we find out from actually using it in the field. Assuming things are still looking up and more villages want this, then we should begin production to produce as many of these as possible. So if you have any questions or want to get involved, please feel free to email me at dixonr0001@my.uwstout.edu.